Okay, in this video we're going to tackle, or attempt to tackle, the integral of the hyperbolic secant of x. And there's two ways that we can go about this. One of the routes is to do what we did in the previous video, and when we were dealing with the hyperbolic secant squared of x, and that is express the integral in terms of the basic definition of the hyperbolic secant. And that's what we did for our first approach. And if we go that way, then we can write the integral like this. That would be 2, and then here we have dx over e to the x plus e to the minus x. That is the hyperbolic secant there. And we can add these together, e to the x plus 1 over e to the x. And that will give us 2, the integral of dx divided by e to the 2x plus 1 divided by e to the x, where that would equal 2 times the integral of e to the x divided by e to the 2x plus 1 dx. And we're looking at this now, and hopefully you're thinking perhaps this can be solved with a u du type substitution. So let's try it. Suppose we call this u. Let u equal e to the 2x plus 1. Now notice if we do that, e to the 2x, that will equal u minus 1, and e to the x, that will equal the square root of u minus 1. E to the 2x equals u minus 1. Let's take our differentials then. Du, that will equal e to the 2x times this differential, which is 2 dx. So dx, that will equal du divided by 2 times e to the x, that's e to the 2x, just dividing both sides of the equation by this, and e to the 2x is this. So dx is equal to du divided by 2 times u minus 1. So let's see. Here we have the plot. This is the integral here. E to the x, that's this. Dx, that's this, expressed entirely in terms of the variable u. And this is u. So it looks like we have all the pieces. Let's put them together and rewrite this integral. It's going to be 2 times the integral of e to the x, that's this, the square root of u minus 1, dx, that's this. So down here we have 2, take that to the outside, times u minus 1 du, and this we call u. So it looks like now we're going to have the integral, here we have the square root of u minus 1 divided by u minus 1. So that's going to be the square root of u minus 1. So that puts the integral in this form. So we started with this integral here. We tried a u/du type substitution, and it got us down to this integral. Has it done us any good? Here we have a radical expression, and integrals that contain radical expressions can be difficult to deal with. We're looking here, this is a variable minus a constant. It doesn't quite fit the typical mode for a trig substitution, but let's give this a try anyway. We have here a variable minus a constant. Hopefully that reminds you of this trig identity, that the secant squared of theta equals the tangent squared of theta minus 1. Here it's a variable squared minus a constant. Here we just have a variable. But let's try this out anyway. We say let u, and we're just going to let u be equal to the tangent squared of theta. Because when we do that, this becomes the tangent squared of theta minus 1, because the secant squared of theta, and we take the square root of that. This now becomes the secant of theta. We know what u is, that's the tangent squared of theta. What about du? So du, put it over here, du will equal 2 times the tangent of theta times this derivative in here, which is the secant squared of theta. D theta. So it looks like we can take this integral and express it in terms of a trigonometric integral. Will that do us any good? Let's check ourselves first. We are saying we're calling u equal to the tangent squared of theta. So this would become tangent squared theta minus 1, which is the secant squared of theta. Take the square root of that. This is the secant of theta. This is the tangent squared of theta. And du will be 2 times the tangent of theta times this differential here, which is the secant squared of theta d theta. So, let's see what happens on this go around. Here we have the integral of du. That's this. 2 times the secant squared of theta times the tangent of theta d theta divided by u, that's the tangent squared of theta, and this is the secant of theta. And what does this give us? Here we're going to have 2, the integral of things like this and this are going to cancel, and this and this are going to cancel. So up here we have the secant of theta, and down here we have the tangent of theta, d theta, and this should be the cosecant of theta. We can show that. We've done this before, in fact. This is the sine of theta divided by the cosine of theta. It's in the denominator, so we take its reciprocal to bring it upstairs. So that's the cosine of theta divided by the sine of theta. This is already in the numerator, but that's 1 over cosine of theta. So we get 1 over the sine of theta. And that's equal to 2, the integral of the cosecant of theta d theta. And we know what that is. This we can integrate. This will equal minus 2 times the natural log of the cosecant of theta plus the cotangent of theta. So it took us a while to get there, but finally we got these whittled down into an integral that we could integrate. Now we have to go back. Let's see, we can go back to here, a previous substitution, and say, well, the tangent of theta that equals the square root of u. And here we know what the cotangent would be. That would just be 1 over the square root of u. But what would be the cosecant of theta? So now, as we've done many times before, we draw a triangle. So we can express this in terms of u. So here's theta. And the tangent of theta equals the square root of u divided by 1. And the tangent of theta is the side opposite divided by the side adjacent. So this is going to be the square root of u plus 1. So let's go back to here. The cotangent of theta, that's 1 over the square root of u. The cosecant of theta, that's going to be this, divided by the square root of u. So here, we have this will equal minus 2 times the natural log of this divided by the square root of u plus 1 divided by the square root of u. So we're going to have the square root of u plus 1 divided by the square root of u. Divide through by this, you're going to have this, that's the cosecant, and this divided by the square root of u, that's the cotangent. But now we have to remember we've made multiple substitutions along the way, and this is what u is. U equals e to the 2x plus 1. So we plug this into here, and we claim that is what this is going to equal. So we have the hyperbolic, the integral of the hyperbolic secant of x dx will equal minus 2 times the natural log of square root u plus 1, that would be e to the 2x plus 2, plus 1, divided by the square root of u, that would be the square root of e to the 2x plus 1, plus an arbitrary constant. And you might be able to manipulate this a little bit more, but the problem is if you look up the hyperbolic secant of x dx in your table of integrals, chances are you're not going to see this expression. We went ahead and posted this video. We don't see anything wrong with this. We don't see any mistakes that we made, but it's not the answer that you're going to see if you look this up in a table of integrals. And to get that answer, we have to use the second approach to the problem, and we'll do that in the next video. It'll be considerably shorter, and we'll try to come up with what is the standard answer, quote unquote. So join us for that video, and we'll try to get another expression for this.